As a reminder, if T is a linear transformation that takes things in the set U, in the vector space U, and transforms them, does things to them, so that they end up in the vector space V, then we've defined the null space of T as everything in U that maps to the zero vector. Everything in the domain, U is an element of U. U belongs to U, or U is in U, such that, or so that, T of U, the answer, if you will, this is like saying X, this is like saying f of X. The null space of T is all the U's in U, such that T of U, for all those U's, T of U is equal to 0. That's what the null space of T is. U, a collection of all the U's and U's for all the U's in the domain for which this statement is true. All the U's that you plug into the T transformation, the transformation T, that return the zero vector. The range of T, we haven't actually talked about this in this kind of detail yet, but I'll just do that now. The range of T is the set of all T of U's. This is the answer, if you will, right? Let's see, how else could I say this? This is like saying X is in the real numbers such that f of X is equal to 0. Down here, we're saying f of X is in the range, right? F of X is in the final vector space, in the resulting vector space. So f of X equals Y, right? If we use our function analogy, f of X is equal to Y is in the resulting vector space where U has come from the domain. So if U has come from the domain, then the range of T is all the T of U's, all the things you get by plugging U into the transformation, and those have all ended up in V. So this is one of the reasons we say that the range and not the codomain, I'll write that down here, the codomain of T is just V, right? That's all the potential answers. It's all the answers that live in the space we're mapping to, but not everything in here may get mapped to, right? There may be some things in here that don't come from a T of U. So the codomain is all of V, but the range is just the T of U's that are in V, where U has come from U. So this is just fancy sort of set notation definitions of things that we already know. Now, just as we did in, I think it was just the previous section, we can find the dimension of the range of T. Let's call it the dimension, denote it, the dimension of the range of T. Once we know that, we're going to call that the rank of T. And here again, we're talking about the rank not of a matrix, but of a transformation. And we can do the same thing with nullity. If we find the dimension of the null space of T, we call that the nullity of T. Your book goes to great lengths to prove this, and in fact, the rest of this section is more information about both the nullity of T and the rank of T. I'm actually not going to go into this in any much more detail than this. Finding the rank of a transformation is different from finding the rank of a matrix, although you can use a matrix to do it. But it's beyond really what we need for this course. I'm including this section just because I want you to see that there is some continuity here, that there is a connection between matrices and linear transformations. But that's really all we need from this section. So if you're watching this video because you're in my class, then at this point you can relax a little bit. I don't really care too much if you follow Theorem 7.3.3, the rank nullity theorem for a linear transformation. I don't really care if you follow example 7.3.1 using the rank nullity theorem for a linear transformation. And in fact, I'm not going to ask you to do the participation activities 7.3.3 or 7.3.4. Let's see what it comes after that. 7.3.5, the theorem 7.3.4, characterization theorem for invertible linear transformations. We haven't talked about invertible linear transformations, so I'm not going to ask you to do that or the participation or challenge activities that follow. So really, the only thing I want you to take from this subsection, if you will, is just the idea that as with a matrix, we can find its null space, we can find its nullity, we can find its range, we can find its column space, and we can find the dimension of its column space, and we call that rank. They are similar, they are connected, they are not the same. But there is consistency, there is practical consistency between the two ideas.